In our study of series, we've been looking at geometric, harmonic, and telescopic series and whether they converge or diverge and under what conditions that happens. And remember that our whole concept of whether an infinite series converges or diverges is based on whether the limit of partial sums converges or diverges. So just to reiterate what we mean by that, if we take an infinite geometric series, whether this series converges or diverges depends on whether the limit of the sum of n terms diverges or converges. So what we did is we found a formula for the sum of n terms. This is it for a geometric series. We took the limit, and if r was between 1 and negative 1, this limit converged to this value. If r was outside of that range, then it diverged. Okay? So the point I'm trying to make is that determining whether any series converges or diverges, we always look at the limit of partial sums, the limit of Sn. However, here's the problem. In most cases, we're not able to find Sn for most series. We were able to do it for geometric, we were able to do it for telescoping, but for most series, we're not going to be able to find a formula for the sum of n terms to take the limit of. Therefore, the question is, how do we determine whether an infinite series converges or diverges? For example, here's an infinite series that I can't find a formula for the sum of n terms. If I look at this series in the calculator, got it represented recursively here, graphically, it seems that I'm approaching some finite sum. In the table, I can see the sum of the first two terms is 1.25. That matches what I have on the screen. Plus a ninth would be that. I can see that the sequence of partial sums seems to be getting close to some value, but I don't actually have a way to find a formula for Sn by which I can calculate these values. So if the series actually converges, which I think it does, the best I'm going to be able to do in terms of estimating the sum of this series is to use an approximation via a calculator or some other computing device. But back to the core question right now, how do I know for sure that this series converges or diverges? I need to be able to calculate this limit. And since I can't find Sn, I can't calculate this limit, so we're going to look for other ways, other tests to determine whether an infinite series diverges or converges from this point forward. So what tests can we come up with to determine whether an infinite series converges or diverges without being able to directly take the limit of its partial sums? Well, let's look back to geometric series for a clue to one of those. Remember that this geometric series, it converged. This geometric series doesn't converge. And the main difference you'll notice is that in the first, the terms are going towards zero, and in the second, they're not. And for a series to converge, one of the basic things that has to happen, I think it makes sense, is that the terms, as the number of terms increases, these terms have to be approaching zero. If they don't, if you keep adding on a larger and larger amount, there's no way that your infinite series is going to converge. So here's one basic test that we use, called the divergence test. If the limit of the terms themselves don't approach zero, then there's no way that our infinite series can converge. In fact, it diverges. If the terms do approach zero, then the series may converge or diverge. Okay, we don't know for sure that it converges. It's one or the other. You might be somewhat puzzled by that, but remember that our harmonic series the terms themselves are approaching zero, but we've shown previously that this infinite series diverges. Now, I can take the converse of one of these statements above, and we can say that if an infinite series converges, then we know for sure that the terms themselves must be approaching zero. So let's consider these theorems in deciding whether this series diverges or converges. So the only test we have at the moment is we're going to take our sequence formula and take the limit as k goes to 0. And we know how to evaluate a limit like this. We know that the most influential terms will be the highest powered ones. So these terms don't matter. K squareds cancel out, and our limit is 2/3. Okay? And since our limit is not 0, we know that the original series diverges by the divergence test. We need to write this out. Therefore, our series diverges by the divergence test. There's going to be a number of tests moving forward, so you want to name the test you're using. The series diverges by the divergence test, and why? Because the limit of the sequence a sub k, we'll call it, this is a sub k, doesn't equal 0. Let's look at another series. Again, we're going to take a look at what the divergence test tells us. We're going to take the limit of a sub k, which is the formula that generates the terms in the series, and the constant won't have an influence. Divide top and bottom by k squared, which leaves me with that, and as k goes to infinity, this goes to 0. So the fact that the limit is 0 tells me that the infinite series may converge or diverge. I still don't know which. I'm going to need to use other tests that we'll learn about later to determine that. So for now, since the limit k approaches 0 of a sub k is 0, the series may converge or diverge. Now there are a couple of other theorems I want to mention that are helpful in helping us determine whether a series diverges or converges. Here's one. Convergence or divergence is unaffected by deleting a finite number of terms from a series. So if your series is going from 1 to infinity and you show that it converges, let's say, then whether you go from 9 to infinity isn't going to change that. So specifically, here's a geometric series that we know converges because the r value is a quarter. If I were to change the index on the bottom to a 9, and even though I've excluded the first 8 terms, I know that this series will still converge. However, what you need to be careful about is that the sum of this will be different than the sum of this. The sums will be different, but the fact that they both converge will still be the same. So you can delete a finite number of terms, and the new series will converge if the original converged, or the new one will diverge if the original diverged. Here's another useful theorem for later. If two series converge, then creating a series in which you add or subtract the two series, that series will converge. And if that happens, then their sums are related as follows. And a final useful theorem, if you have a non-zero constant, then the sum of a series as well as a constant times the sum of a series will act in the same way. They will both converge or they will both diverge.